Hi everyone, I am Cristian Riveros from the Catholic University in Chile and part of the Millennium Institute for Foundational Research on Data. Thanks for the invitation to the workshop of races. And the title of my talk is A Theoretical Approach for Complex Event Recognition. And actually, I should add here for query languages. Yeah, because really this talk is about the formal aspect of query languages in complex event recognition. And this brings me to my motivation. Basically, it has been this long criticism to complex event recognition query languages that I resume in this citation of Kugola and Margara that basically says that such languages are often oversimplified, providing only a small set of operators. Even worse, and here comes the most important part, the semantics of such languages is usually given only informally, which lead to ambiguity and make it difficult compare the different proposals. Well, if you are in favor of this statement or not, okay, well, there are other papers that also state the same, one from the 1990s and one very recently in depth 2017. Yeah. So basically, there have been systems and query languages, but the formal aspect of these languages has not been studied properly. So the question here is, well, what do we expect for a query language for complex event recognition? And the first is that we want a formal and syntax and semantics. For every query and string, basically the output will be defined precisely. Second, we would like to have a declarative language that the user will declare what he wants and not how to do it. Third, we want a language that is denotational. This means that the semantics will specify what is the output and not how to compute it. And last but not least, we want to be composable. Not all languages in complex event recognition are composable, and this means that the operators can be combined as free as possible. Well, these four aspects are part of the reasons why languages like SQL are so relevant or so useful. Yeah, basically they have a formal syntax and semantics. They are declarative, they are denotational, and composable. So the question here is, can we have a complex event recognition query language that satisfies these properties? And this is the goal of my talk. I want to present a logic that has the four properties that I stated before, a logic that we call complex event logic. When I have this logic, I would like to understand some features of these languages like selection strategies. Yeah? And then I will introduce an automata model for complex event recognition that will allow me to compare the expressive power of these formalisms. Yeah? This is my goal, my idea, is to give a positive answer to the statement of Kugola and Margara. I'm not alone on this. Yeah? This is a joint work with these three guys, Alejandro Gres, Martin Ugarte, and Steen van Sumeren. So the outline of my talk is basically what I said before. I'm going to define formally what is this logic for complex event recognition. Then I will talk a bit about selection strategies. Then compare the expressive power with an automata model for complex event recognition. And finally, the conclusions and open questions. So let's go with the language. First, the data model. Basically, I want to define a stream that is no more than a sequence of events where each event is represented as a tuple. Here, a tuple, I mean a relational name, an attribute name, and an attribute value, as you know. Yeah. Here I will drop the attribute name because it will not be useful for the examples. So usually I will have just a relational name and some data. So the stream basically is a sequence, okay, of tuples, T0, T1, and so on, indexed by their position, and these tuples are also called events. We are in complex event recognition, of course. And basically a stream will look like this sequence, okay, of tuples. Yeah. Here I'm thinking that I will see the first tuple marked with index with 0, then the second tuple, and so on. Okay. Of course, I'm thinking here that I will read this stream of events, okay, from left to right. For the sake of simplification, I will simplify the representation of this stream. So usually I will have, from now on, just tuples with one attribute name, and actually sometimes I will drop all the attribute values in order to have just something like this. It's for the purpose of the talk, in order to have a simple examples. So what is a complex event then? Well, a complex event is just a subset of events. Yeah? If and I can define this formally. Basically, a complex event is a non-empty finite set of positions, given that tuples are indexed by position. Just this position is enough to define in a unique way a complex event. So basically, if an event is just one of these tuples, then a complex event is a subset of them. Now that I have the data model, I can start to define the logic. Yeah? Basically, what I want with a formula is that giving an input, that it will be a stream of events, I want to produce a set of complex events. Basically, as if I have my input, the stream that I had before, then, well, I would like to have a logic that allows me to define a complex event like this one. But it's not going to be only one complex event that satisfies my formula, or that my formula can produce. Well, there can be many of them, and that's why the output is really a set of complex events. Yeah. In other words, a self formula recognizes complex event and extract them. Here I want to emphasize that this is not a Boolean logic. Basically, this is a language actually that is for define complex event and output them. So let's go to the syntax of the logic, starting from the atomic case, that is basically R, a relational name. Then we have the three most used operators in complex event recognition, that is the sequencing, the OR, and the iteration, that is some sort of clean closure. And then we have variables that are assigned with the operator in X, and a filter operator that allow me to use a predicate over the variables. Basically, the idea is that with a variable, I will capture a complex event, and then I can compare this complex event with this predicate P. As an example, a self formula is something like this, where I can combine freely the three operators, and the in, okay, that is applied to over any formula, and the filter. Notice that this logic is composable, as we defined at the beginning. Basically, I can define freely, I can apply freely all the operators. Yeah? It's important to start to notice that the variables in CEL actually represent set of events. Okay? Basically, a variable will capture a complex event. I will define this more formally in a minute. Yeah? When we define the semantics. First, a definition for the variables. What is a variable assignment mu? Is basically a function that maps variables to complex events or sets of positions. Basically, a variable x is mapped to a finite set mu of x, that is a set of natural numbers. Then, informally, what's going to be the semantics of CEL? Basically, it's going to be a function that maps a stream and a variable assignment to a set of complex events. Basically, this semantics of phi of s and mu will give me all complex events C of stream S that satisfy phi given mu. Here, again, I want to emphasize that a SEL formula recognizes complex events and extract them as output. So let's be a bit more precise, and I will define each operator formally. It's not very difficult, starting with the R. Yeah? Basically, given R will give me all complex events that have only one position. This position has the attribute, the relational name R, and the mu is assigning each variable to the empty set. Basically, I'm not capturing anything in the variable yet because I haven't defined a variable. For example, if I have phi equal to R and I have this stream, then what you will expect is that this will give me all complex event of one event that has the relational name R, like R0, or the complex event that just contain R2 and R3 and so on. Yeah? So basically the atomic case allow me to extract a complex event of just one event. How to define sequencing? Well, basically the idea is that the sequencing of phi1 and phi2 will give me all complex events C such that I can divide C into a complex event C1, that will be the output of phi1, a complex event C2, that will be the output of phi2. Well, both together form the complex event C, and I want C1 to be before C2. This means that the maximum of C1 has to be strictly less than the mean of C2. Let's give you an example, and it will be more clear, the definition. Basically, if I have my stream, I want to evaluate the query R followed by T, then this will give me, of course, all the complex event of R followed by T, like R0 and T1 will be a complex event for this query, but also two events like R2 and T4. Basically, the idea of this sequencing operator is that it allows me to skip an arbitrary number of events. Yeah. Usually in complex event recognition, streams are noisy, so it's very difficult that you will find R and T, okay, consecutive in the stream. And that's why the sequencing operator is usually defined as this, that you can is allowed to skip an arbitrary number of events. And another output is R0 and T4 and so on. Okay, yeah, you can see that all R and T's, okay, that are one followed by the other is going to be given as outputs. About the disjunction, well, this is not very interesting. Basically, it will output all complex event C such that C is in the output of phi1 or C is in the output of phi2. Yeah? It's just a normal disjunction. What's more interesting is the iteration plus. How we define this here? Well, as it usually defined in a regular expression, as the clinic closure of phi by using sequencing. Basically, the union from k1 to infinity of the semantics of vk, where vk basically is the sequencing of phi k times. Yeah, so let me give you an example to see how to use this operator. For example, I want to see a complex event that is a T followed by one or more R's and then followed by a T. Well, one possible output here, okay, of this is the complex event that is there, yeah, T1, R2, R3, and 4, and then T5. But similar as for the sequencing operator, this iteration is allowed to skip events, an arbitrary number of them. So also T1, R2, R3, and T5 is part of the output, so I can skip R4. And given that I'm saying one or more, well, this is also a complex event that's going to be part of the output. Yeah. So this is the idea of iteration, but given that I can skip any event that I want, then I can have this kind of complex event. Of course, this is a problem. Maybe the user doesn't want all the possible subset of R's that it can extract. And I will see how to solve this in a minute. So wait for this. And so on. So we have the semantic of these three operators. So how we define variables? Well, with this mu, the idea is that the variable assignment will capture the complex event that is produced by phi, okay, in his variable x. So basically, it will give all complex events c, such that mu of x is equal to c, and c is part of the output of phi of over s, and mapping assignment mu prime, such that it coincides with all the variables different than x. Yeah, basically saying that in mu I will capture the complex event c that is bound by phi. For example, suppose that now I use x to capture the sequence of R. Then, well, now I need to define that mu x is equal exactly to R2, R3, and R4. And if this is the case, then these are going to be part of the output. Yeah, this complex event here, and also this complex event here. Note that given that mu is used as an artifact to store the complex event that is in between, okay, R2, R3, and R4, well, only the complex event that have these three elements will be part of the semantics of phi. So now that we can capture complex event in the variables, well, I can filter them. For this, I need to define what are the predicates that we can use in the logic. And for this, we consider what we call universal predicates. Predicates that are of the form, basically, for all t1 in x1, and so on, and for all tn in xn. These predicates p of e of t1 to tn is satisfied, where this pe is a first order predicate over tuples. Now this is basically a technical definition. Let me give you an example. So suppose that I want this this predicate that has only one variable, and says that all the tuples that are in this complex event must have ID equal to 11. Or I can have this other predicate that is the same ID of x1 and x2, and it says that all events in x1 and all events in x2 must have the same ID. It's important to notice that the definition of CEL actually considers any predicate over set of tuples, but in this talk I will restrict to these universal predicates to fit our purposes. Most of the results that I will state in a minute are assuming that we're using these universal predicates. Yeah? But in general, we can use any predicates over complex events. So now that I have these predicates, basically what is phi filter of p is all the complex events c that are part of the output of phi, and such that the assignment of the variables x satisfies p. Yeah? Basically, with this filter, I can use the variables to filter complex event. As an example, suppose that now to my query, I now add the filter of same ID of x and x. This is not an error. Basically, what I'm saying here is that all events that are in x must have the same ID. Then, if I have my string now with the data inside, okay, with the IDs, then if mu is mapping to R2, R3, and R4, well, the complex events that I have before are not part of the output. Really, the output is going to be empty because this mu of x is not satisfying the predicates as it says in the definition. But if I remove the element in between, then now these complex events are going to be part of the output, and as I expect, okay, all of them, okay, will have the same ID. Yeah, well, all in the complex event. So this is the definition of the semantics, yeah. But really, this mu is used as an artifact to define the assignment of the variables, yeah. So the output of a formula, really the final semantics, at a position n is defined as all complex event C such that the maximum element, the last event, is equal to n, and there exists mu such that the C is part of phi evaluated over S and mu. As I said, mu is just an artifact to define the semantics, and we can drop it when we give the final output that are the complex events. Okay, so actually this logic cell is a good representative of many complex event recognition languages. An example is SASE. For the design of this logic, we base or design in SASE, and you can see that they use this sequencing operator, the clean closure, the assignment of variables and predicates similar to CEL, okay, and have some sort of universal predicates to define this less equal. But not all languages are like CEL, okay? Some languages are not represented by CEL, like Cayuga. They use variables in a way that they are assigned to events. Yeah, basically these dollar symbols here basically assigned to events, and they check the value directly, and they have some way to iterate over them. Yeah. So basically, system like SASE treat variables as set of events, and this is similar to CEL. That was the purpose. But there are some other systems like Cayuga that treat variable as events. Well, really, I cheat you because we have two versions of CEL. One that is called Set-CEL, and another one that's called Event-CEL. Set-CEL is exactly what I defined before, how we use the variable, like set variables. And it's what I defined this talk, and it's defined in the paper of this year in ICDT. And Event-CEL, we define variables as to store events. These variables are defined directly in the atomic case, in the relational name, and they capture events in order to compare them. This Event-CEL is defined in a paper of last year, ICDT. And well, given the short time, I don't have time to define it, okay? But I want to state a theorem, how we can compare them. And the theorem says that over unary predicates, Set-CEL is equally expressive than Event-CEL. So if you just use unary predicates as this ID 11, well, you can use variables as in Cayuga or in SASE, and there is no really difference in the expressive power. But if you use binary predicates, we show that Set-CEL is even more expressible than Event-CEL. What is strange is that if you move to ternary predicates, well, these two logics are incomparable. The reason why they are incomparable is that it's not only the way how you define the variables, it's also the way how you define the iteration, this clean closure. And the definition is very different when you are working over events. You have to iterate, like in Cayuga, and this allows you to define other complex events. I can't say more, I don't have too much time, but for more details, please see the paper of this year in ICDT. So this is the logic. Now that we have a query language, a formal query language for complex event recognition, we can study features like selection strategies. So first, a motivation. We already see that we have a problem with multiple outputs in complex event logic. For example, if I have this query, similar to what I have before, an R followed by one or more T's and a U, well, I can see that this is going to be part of the output, and is what I would expect or would like to extract when I see this U. But also I will have that this is going to satisfy my pattern, because it's an R followed by one or more T's and a U, and also even this output that has the same sequence of T, but the first R that I see is R2. Well, the question that people from complex event recognition system ask is, which complex event would you prefer as output? Well, to solve this multiple output problem, people insert system operations to filter the complex event. And these are called selection strategy. The problem is that these selection strategy are usually defined by an algorithm or very informally, and the user doesn't know what this really means, this algorithm. Yeah? As an example, in SASE, they define this selection strategy that is called skip till next match, and it's also defined in other systems. And the definition basically says a further relaxation is to remove the contiguity requirements. All irrelevant events will be skipped until the next relevant event is read. So the question here is, how can we formalize the idea of skip irrelevant events? Well, the advantage to have a formal language and formal model is that we can now define this idea of skip till next match by using an order. So for this, I will use the symmetric difference between two sets. That is basically all events that are in C1 and not in C2, or in C2 and not in C1. Then we define the next order to define this skip till next match in order to compare two complex events. And the idea is a bit weird, but you will see that it makes sense. Basically, I will set that C1 is less than C2 if, well, they are the same, or the minimum of the symmetric difference is in C2. As an example, suppose that I have these two events, 367 and 347. Well, you can see that in this order, 347 is after, or is bigger than 367, because it has this 4 that is not, that in the symmetric difference is in the second complex event. Actually, if I compare 347 with 3467, well, I see that the symmetric difference only have 6 as part of the output, and this is going to be in the second complex event. Yeah? So note that if C1 is included in C2, then C1 is less than C2 in this event. This is the idea of skip till next match, yeah, in the sense that you want the complex event that has event that is more to the left, okay, in order to skip them. Well, what is the idea of this is that actually this weird order of next is a total order between complex events. And well, what is the goal of this lemma? Well, is that given that it's a total order, if I have a finite set of these complex events, we can always find the maximum complex event and define the idea of skip till next match. Basically, we define a selection strategy that we call next. And basically, giving a formula phi, we define the next of phi, such that the semantic will give me all complex events C, such that this C is a maximum over all complex events that ends in the last position, basically for all C primes in the semantics of phi. If it has the same maximum position as C, then it must be less than the complex event C. As an example, suppose that I have my multiple output problem as before. Well, if I apply the next operator, I will see that only this is going to be part of the output. And this is exactly the output of this operator skip till next match wants to give. Yeah. So the takeaway here is that when we have this formal semantic, we can start to define this selection strategy in a formal way and understand what they want to say, okay, and define it in a, how to say, in a denotational way, not defining how to compute it, but what should be the output. Actually, we can do even more because we can define new selection strategies. And here what we do is that we, instead of using this order, we can use the containment relation. Yeah, basically doing the same as in next, but modifying the order with containment. We can define a selection strategy that filter the complex event and give me the ones that are maximal elements in terms of subset relation. For example, if I have my multiple output problem, now if I apply max, well, I will have a bit more of complex event than with next, because now this other complex event that is a maximal complex event in terms of containment will be given as output. So basically what I wanted to show with this is that when we have this formal logic and formal model, then we can start to define this selection strategy in a very precise sense. Now that we have this, we can start to move to another way of defining complex event that is usually used in a search system, that is by the use of automata. So what we define is what we call a complex event automata. And for this, I will use P1 to denote the set of all unary predicates over tuples, not over complex event, but over tuples. Then, basically, what is a complex event automata? It's a tuple A that contains a set Q, that is a finite set of states, as usual in an automata model. We have a sets E and F that are the initial and final set of states, and a transition relation that are tuples of states, predicates, a mark that can be black or white, and a state Q. So just let me give you a figure and you will understand what these machines are. Basically, they have states, they have transitions, and you can see that the transition has a predicate and a mark that can be black or white. Here with true, I mean that is the predicate that is satisfied by any tuple. And here the PR and PT basically are filtering tuples that have relational name R, and PT are filtering tuples that have the relational name T. So basically this automata, what is modeling, are all complex events that are an R followed by a T. Let me explain this a bit more formally, okay, with a figure. Yeah? Suppose that I have a stream. So how we execute this complex event automata over the stream, basically we start from the beginning with the initial state. And when we read the first tuple, well, the automata in Q0 decide if he takes the loop or the transition, the black transition that we said, that goes to Q1. So if we take this transition, the black, then we mark them. Okay, we mark R0 with a dot. And now that we are in Q1, we can take the same decision. We can take any of the two transitions. Suppose that I take the black one again and move to Q2. I reach a final state. Well, this means that this run produces an output that is this R and T. That is a complex event. But this automata is not deterministic, so in the first tuple, he can decide to take the white transition and stay in Q0. Yeah? And now, well, T doesn't satisfy the predicate PR, so he has to stay there and mark it with white. But then, when he reads the R2, he can decide to move to Q1 and mark it with the black dot. And so on, okay? In Q1, he read R, again, he cannot take the black transition, he has to stay in Q1. And then when he reads D4, he fire the black transition and mark the D4 with a dot, giving that we reach a final state, okay? Basically, this is a run, an accepting run, and now he produced the complex event R2 and D4. This is the idea of the complex event automata. Given that I don't have much time, okay, I go to the paper to see the formal definition. But basically, these automata define sets of complex events similar than the formulas. Yeah. So, well, what is the purpose of this complex event automata? Well, of course, the idea is that they are an intermediate model for defining and optimizing cell formulas. Yeah. Basically, what we show is that for every cell formula with filters over unary predicates, well, there exists an automata that define the same set of complex events in each position, in each position n. Furthermore, we show that for any of these selection strategies, next and max, there exists an automata of the selection strategy applied over the formula phi such that it defines exactly the same set of complex events. In other words, selection strategies can be encoded into automata model and not as an algorithm. Basically, it says that if we know how to evaluate complex event automata, well, we can encode the selection strategy inside the automata model. And the second purpose of this automata is to evaluate formulas. Yeah? Basically, what we show is that this automata can be evaluated in a streaming fashion with constant update time per tuple and constant delay enumeration. I don't have time to define this notion, but believe me that these are strong guarantees of efficiency for complex event recognition. Yeah? Basically, we show algorithms that have these guarantees for evaluating this kind of automatas. So it has good algorithmic properties. So every formula can be defined by this automata. Yeah. The question is, can we capture the expressibility of this complex event automata by using the logic? Yeah. And of course not, because the automata have the ability to see two events consecutive, okay, and the logic cannot do this. So in order to capture the expressibility of SEA, basically what we do is we extend CEL with the operator needed to capture exactly the expressibility of this automata. For this, well, you will expect that we need a more strong notion of sequencing, that is strict sequencing, that allow me to don't skip an arbitrary number of events and to see them together. Also, we need some sort of checking when I evaluate this in the starting position, because the automata can see what is the first event in the stream. And finally, but more important, is that what we really need to capture the expressibility of automata is to have an operation for projection. Yeah? That basically, giving a sequence of variables, says that I will just keep the events that are captured in this variable. This is exactly how projection works in SQL. It's the same idea here. So if you extend the logic with these operators, what we can show is that every automata A, there exists an extended cell formula phi of A with filters over unary predicates such that the output of the automata is the same as the output of the formula in each position n. So basically, extended CEL has the same expressive power as SEA, and if you use extended CEL, you can evaluate it as efficiently as these automatas. Yeah. So this is the idea, okay, how we can start to compare the expressive power of different versions of the logic and different versions of these automatas. So this is what I wanted to show, okay, how basically we trying to give an answer to this statement of Kugola and Margara and other papers in a complex event recognition. Really, we believe that CEL and SEA is far to solve this problem of semantics in the complex event recognition languages, but at least it's one step towards formalizing and understanding these languages. Yeah. So just to finish, some open questions. Actually, there are several open questions here. I just will state some of them here, and we can discuss it during the questions. First, well, what is the right language of CEL when we are using binary and ternary predicates? I showed that Event-CEL and Set-CEL are incomparable when we move to ternary predicates. So how we have a language that includes all the levels of variables. Another question is how we add aggregation, okay, etc. Yeah. For example, also how we model time in CEL. We model time here as a sequence of events, but there are more different versions of time in complex event recognition. And finally, well, what is the right computational model when we start using binary predicates? SEA will restrict it to unary predicates, where Event-CEL and Set-CEL are the same, but if we start using binary predicates or other kind of predicates, well, the model of automata is not enough to capture the logic. So this is what I wanted to show, okay? So thanks, and I'm happy to receive your question.